Okay, today's weather is cloudy with a partial chance of rain, so what better way to wake ourselves from this stupor than by doing a partial differential equation problem? And here's the following one, right from the Stewart's Early Transcendentals Multivariable Edition. We want to show that for this particular partial differential equation, so we want to show that the sum of the second partial derivatives with respect to our multivariable functions from x1 to xn equals our exact same function itself, where the function we're dealing with is u of x1 to xn equals e to the a1 x1 plus dot dot dot. And you continue this pattern for any linear combinations of ai's essentially multiplied by xn's. And you're given the additional condition that for these coefficients, a1 to a sub n, that they follow this relation. So the sum of their squares equals 1, essentially. And so now, let's go and get to solving it. Remember, the thing about partial derivatives is that when you take a derivative, you have to take it with respect to one variable only. And then you leave all the other variables constant. So this is exactly what we're going to do. And for shorthand, I'm just going to be using del of u over del of x and xi, which is xi being any elements. Anything element from x1 to xn. Okay. So let's go and do this out. If I do it, say, for a random x1, but we could generalize it for any x within that interval, we'll end up getting that, let's see. Well, we'll get the original function back because it's a natural exponential function, right? So we get this guy and leave him alone. And yet, at the same time, while differentiating with respect to x1, we have to use the chain rule and bring out the coefficient that's right in front of ax1, or any xi. So we bring out a1 in this case. This is multiplied by a1. And you follow this, you can see easily that for the second partial will have an extra a1 factor comes out for the chain rule. So I end up with a1 squared. And then hopefully you can see without loss of generality that the same pattern applies from all x1 to xn. So what I'll simply end up with is the following. So simply, the left-hand side of the partial differential equation now becomes a whole bunch of these exponential terms being multiplied by a1, a2 squared, an squared, an minus 1 squared, all those coefficients squared respectively. But well, we can immediately factor out this exponential multivariable function. And then we're left with the sum of the squares of our coefficients left here. And note that this quantity is simply nothing but 1. So we get 1 multiplied by this exponential function, but indeed that is the original function, the original test function that we wanted to show was the solution. So indeed, this statement holds true. So indeed, ladies and gentlemen, that is one partial differential equation problem solved on a partially cloudy day with a chance of rain. I hope you enjoyed this video. Until then, see you.